So again, do you guys want me to make it bigger, or was this okay for you last time? This form? Is okay? All right. So if it gets too tiny for someone, just let me know and then just switch this, okay? Just at least cable I use, the better it is. Okay, so let's see. Yeah, no, Franklin, I'm talking to everybody here in the classroom. The thing is that last time I left the screen the way that you are seeing it. And I wanted to see if it was okay for them, that way I don't have to be switching back and forth. But it looks like it's okay, so just keep with it. All right, so last time we talked about area, right? So again, we are looking at a little bit of application of integration before we start looking at more techniques of integration. So we discussed area between curves, and let us now begin talking about volumes, okay? Section 2.2, and the volume discussion is gonna be divided into several cases, okay? So first, of course, when we talk about volume, that means we're talking about three-dimensional objects, right? The solids, and then we want to know the volume of these things. So the first thing that we're gonna discuss is how do we find the volume of solids that we know the cross section of. So what do we mean by a cross section? Imagine that you have this solid, and then I slice this and take the slice. What type of slice do we get for this one? For this bottle? Okay, so for those on on Blackboard, I have a bottle of water in my hand. Okay, cylindrical bottle of water. So if we make a transversal cut, right? So that's what we mean by a cross section. We make a cut, and then we look at that slice, we get a circle, right? So we know the cross section of this. Okay, that's what I mean by volume of solids with known cross section. So we already have the solid given, and then when you make a slice, we know how it looks. Okay, so let us talk about how to find the volume of something like this. Then we're gonna move on to other type of solids that we may not be aware exactly how the cross section looks like, but they are produced by a method called revolution, solids of revolution. So when you have a region in the plane, like for example, how can you create a basketball? You can take half a circle, if you want, okay? And then let's say here is a X and Y axis, and then you can rotate this region with respect to the X axis. If you take this half a circle and you rotate, then you're gonna be generating a three-dimensional solid, which would be a ball and a sphere. Do you understand this? So then, after we discuss this, we're gonna move to this type of solids. How do we find the volume of solids generated by doing this type of what do you say? This type of thing, or you know, getting a region and rotating a region about a fixed line that we call axis of rotation. Okay, that's what we're gonna look next. And then there are several questions there. There are some solids that are, you know, just solids. They have no holes in them, and you may have solids with hole, with some cavity in it. Okay, then we're gonna discuss how do we compute the volumes of those type of solids. Okay, so that's what's gonna happen in this couple of sections. That's section 2.2 and 2.3. So right now, let's begin with the easy part, which is we already have the solid and we know the cross section. Okay. I could just give you the formula, but there's no fun in doing that. So let's try to think about how this formula comes to be, and that way, hopefully, we understand better what we're doing. Okay. So I'm gonna try to use something. I usually bring it, but I didn't. Mine was already spoiled. I had to throw it away. I usually bring a loaf of bread that's being sliced already to illustrate what I'm about to do. So I will try to draw it. I'm not Picasso, so use your imagination here, okay? So again, the idea is that we have a solid and we want to compute its volume. I'm gonna draw one solid. I'm gonna use a bread as an example, okay? So let's see. I'm gonna try to do something here. This guy. Then this guy. And actually, I don't want this over here. I see a bread. Do you see a bread? Okay. You need to, if I already tell you what it is, then you probably can. Okay, so imagine that you have a solid like this, okay? And we want to calculate the volume of this. What would be one idea? The idea that we're gonna use is the following. We can go ahead and we can cut this into a bunch of little pieces, okay? So instead of trying to calculate the whole volume, we can just cut into a bunch of little pieces, figure out what's the volume of each of those pieces, and then we add them together. Do you understand this? So imagine that we go ahead and we slice this bread, okay? So for reference, I'm gonna put here my axis. Let's say this is the x-axis, this is the y-axis. As usual, this is A, this is B. Then I'm gonna go ahead and slice this bread. Okay, now the slice, let's take it with some sort of thickness, okay? So there will be a little thickness attached to it. And then we have this. Okay, so think of this as a little slice of the bread. And then, really what I'm doing is I'm slicing the whole thing. So this is just a typical slice, but imagine that this is being sliced completely. I'm just picking one of those, okay? So that's equivalent to say that I'm partitioning this, right, into a bunch of little intervals. Each interval determines the thickness of each of the slices. Do you understand this? So we have n slice. So the thickness, because I'm slicing with respect of x, notice that I'm making my cuts perpendicular to the x-axis. So I'm moving like this from left to right. I'm gonna call this delta x. If you decide to do the slices like this, then you're doing with respect of y. So you will call it delta y, okay? Anyways, I'm just gonna call this delta x and then make the observation that V is the volume of the solid. Then I'm gonna call VI the volume of the ith slice. There are n slices, okay? So this is what I mean by the ith slice. So with this notation, it's clear that V is equal to the sum of these volumes, okay? Now, of course, the point is that we don't really know what's the volume of this slice either, okay? So what we can do is we can approximate this volume. Now, if you look at this slice, if we make it very thin, you can actually think of this as being approximated by some sort of rectangular solid, okay? I know it has a little curvy thing on top, but we can actually approximate that with rectangular solids. And the reason why I'm bringing this up is because every time that you have, okay, I don't have a book here, but okay, imagine that this iPad is a book. And think of this as being a little bit more thicker. How do you find the volume of this? So length times width times height. Now, what's length times width? Area. The area of the base, right? So every time that you have a uniform solid, that the base is the same, we call this in general a cylinder. The base is whatever shape you want, but it's always the same, and then it just goes up, right? And you cut it at some point. You can find the volume by doing area of the base times the height. Do you understand? Do you understand this? And by height here, I mean the thickness, like how thick this is. So area of the base times the thickness. Do you understand this? Okay. So we can actually approximate. So we may approximate the volume VI by, because of this picture, okay, I'm gonna say some sort of rectangular solid. Okay, think of as like a little book or something like that. Okay, so the point is that this volume can be approximated by the formula area of the base times the thickness. Okay, now this area of the base, let's give it a name. I'm gonna call this AI, and the thickness, we're calling this delta X. Okay, now as you know, it really depends where we did the cut, because if you do the cut close to the beginning or the ending of the bread, then we have a smaller little slice. We have smaller slice than if you do it in the center. So as X changes, this area is going to change, and so with the volume, right? So this really depends where you're making the cut. So it's a function of x. If this picture, if you're doing the cut perpendicular to the y-axis from top to bottom, then it will be a function of y, okay? So in this little interval, let's call some, I don't know, let's put ci in here. So then this is really a of ci, and this is really b of ci, right? Because it depends, ci is a point inside the interval because it tells me the ith slice. The thickness is always the same. So now you should see what's going on. So if we want to calculate the whole volume, we know that it's equal to the sum of the volume of the slices, but each of these can be approximated by the formula. AI of CI times delta x, and remember that here delta x is, as usual, b minus a over n. Same thing that we did when we're talking about areas. If you want to calculate the sub-volume, then what we can do is we can take infinitely many slices, right? And then that means we're going to take the limit as n approaches infinity of this expression. So the volume equals the limit as n approaches infinity of this expression. Okay, and then, as you know, what is this? What's another fancy way of writing this limit?
An integral.
This is an integral, right? This is a Riemann sum, right? This is your function, if you will, right? This is the function that we will be integrating. This will become dx, and then, because this is a Riemann sum, this is an integral from a to b, because our interval of partition is from a to b. So this is the same as the integral from a to b of the area function dx. Now, what's a of x? This is the area of the slice, right? This is the area of the slice, which we call it cross-section in this language. So where a of x is the area of the cross-section. Did you understand this? So again, at the end of the day, you just need to remember this formula, okay? And I'm trying to let you know where this formula, why do we even think about this formula, okay? And the whole point is that you can calculate volume by doing area times thickness. Area of the base times the thickness, okay? dx, remember, is the thickness that when we take infinitely many slices, the thickness is very small, infinitesimal, and then you really just integrate the area. The integral is really a sum. It's like an infinite sum, okay? So just adding all of those little pieces together is what we're saying. Okay. All right. Questions? Now, the formula is like this because we were doing it with respect of x. We were doing our slices perpendicular to the x-axis, but we could do it from bottom to top, perpendicular to the y-axis. We could slice something like this, like if you put the bread standing and you slice like that, okay, perpendicular to the ball in this case, for example, we will be doing the same thing, but with respect of y. So we have two formulas for the volume, one with respect of x, another one with respect of y. So let me write down the theorem. So theorem, suppose, so let V be the volume of a solid with known cross-section. So what I mean by this is that we have somehow a way of figuring out a formula for this area, okay? We know the cross-section. It could be a triangle, it could be a circle, whatever, as long as you can figure out the formula, okay? So let V be the volume of a solid with known cross-section over an interval. Then number one, if the cross-sections are taken, does everybody knows what the symbol is? No, perpendicular, right, from geometry. So instead of writing the word perpendicular, I'm gonna write that symbol. Yes? So as perpendicular, and this is, what's the symbol? As for parallel, right? And we say that lines are parallel. So let me just write it for For your own information, this means perpendicular. Okay, so if the cross sections are taken perpendicular to the x-axis over the interval AB, then the volume of the solid can be calculated by doing the integral from A to B of A of x dx, where here A of x is the area of the cross section. It's a function that gives you the area of the cross section. Tell me where you're making the slice, and then I'll tell you the area. And then similarly, if the cross sections are taken with respect to, perpendicular to the y-axis, if the cross sections are taken perpendicular to the y-axis over some interval, let's call it CD, then the volume can be calculated by doing the integral from C to D of A of y dy. So same formula, it's just that now instead of with respect of x, we're doing it with respect of y, okay? Where here A of y, once again, represents the area of the cross section. This is really what you need to know. That you integrate the area, that's going to give you the volume. You okay with this? All right, so then let's do examples. Let's see. Examples. So I'm going to do one basic example first to see how this works with some actual functions. And then the second example, let's apply this idea to prove one of the formulas that you know from high school. For example, from high school, you know volumes for pyramid, sphere, circular cones, right? So you can use this idea to actually justify those formulas to see why these formulas work. We're going to do it for the pyramid. We're going to figure out formula for the pyramid. All right, but first let's do one regular example just to warm up. All right, so find the volume. Find the volume of the solid. Now I have to tell you something about the solid. So with base given by the region. So given by the region bounded by the following functions. F of x equals 1 minus x over 2. G of x equals -1 plus x over 2. And x equals 0. So that's the y-axis, okay? So I'm telling you again, you don't have to draw a solid, and I'm not going to draw a solid because that's not an easy thing to do in general if you're not good at drawing. But you do need to draw at least the base and then try to imagine the solid. I'm going to show you how we can do that, okay? Now I need to tell you how are the cross sections, because until I tell you the cross section, you cannot really think about the solid. So this is the base of the solid, and then the cross sections. The cross sections perpendicular to the x-axis are going to be equilateral triangles. Okay? All right, so to really understand what's going on here, I mean, I didn't give you an interval, so you really need to do something to figure out the endpoints. But just with the information that sections are equilateral triangles and perpendicular to the x-axis, you could go blindly, and then you know that you have to use this formula. You put here the formula for the area of an equilateral triangle, and you integrate it, you're done. But of course, you have to find A and B. You can do it by playing with the formulas, but it's good practice to actually draw the region. Okay, so that's what I'm going to do. I'm going to sketch the region to really understand what's happening. All right, so let's see. F and G, they are both lines. So the first one is the slope is -1/2 and the y-intercept is 1, right? So it goes through 1. Let's say 1 is here. And then the slope is -1/2, so it's going down. And we know that 2 is the x-intercept, right? If you put x equal 2, you're going to get y equals 0 here. So that's 1, Let's say this is 2. So this is 1 point. This is another point. And we have our line. Okay, so as F, then we have G is also a line with slope positive a half, so it's going up, and it passes through -1, so on the y-axis. So here is -1, so it passes through this point, and then once again, 2 is also the y-intercept, right? So it also passes through 2, but this time the line is rising, so it looks like this. I want it blue. Okay, so that's G. So that's the line G, and then the region is also bounded by the line x equals 0. That's the y-axis. Okay, so we're talking about this triangle right here. This is the base of our solid. That's the base of our solid, and then we're being told that the cross section taken perpendicular to the x-axis, so meaning we're making the cut like this. You understand this? So cross section perpendicular to the x-axis, we're making our cuts like this, are equilateral triangle. Now here we're seeing the two-dimensional picture. So the solid this is the base of the solid. You have to imagine the solid as coming out of the board, out of the, let me say screen. This is screen, and on blackboard there's a screen. So imagine the solid coming out of the screen, okay? But in such a way that every time that you cut it like this perpendicular to the x-axis, you take out an equilateral triangle. So the solid is really, you know, coming out like this in a triangular way, but it has a line like this. So every time that you cut, the slice is a triangle. Do you understand what I'm saying? Again, you don't really need to draw it. If you're good at drawing, then you can draw it. But you don't really need to draw it. You just need to understand. And we're being told that every time that we make a slice, we take it, we have equilateral triangles. Okay? Now, do we really need to know more about this solid? Let's see. We need to understand the slice. The slice is an equilateral triangle, so the other two sides of the triangle are coming out of the screen like this. Yes? Now, this is one side of the triangle. Do we really need to know these other two sides? No. We don't, because it's an equilateral triangle. What does that mean? All sides are the same. So as long as you know what this is, then you can figure out the whole triangle. Do you understand this? So now our job is to figure out the area of such a triangle, right? Because as you know, now that we have this, and by drawing the picture, we immediately see that our interval is going to be from where to where? From 0 to 2, right? Because we are slicing, starting from 0, we are slicing like this, all the way up to 2, right? So the volume that we are after, we know that's going to be the integral from 0 to 2 of a of x dx. Now here, a of x is the area of an equilateral triangle. I'm saying a of x because, you know, notice that depending what x is between 0 and 2, the length of this side is going to change, right? So you're going to have smaller, if you move towards 2, you're going to get smaller and smaller triangles. You understand this? The closer you are to 0, the bigger your triangle will be. Okay, so this is the area of equilateral triangle. So let's have a little talk on this. Does anybody remember the formula for this? Area of an equilateral triangle? Yes?
1/2 base times height.
Okay, but do we know the height? So the area for any triangle is 1/2 base times height. Do we know the height of this triangle? The thickness is this dx. So we just calculate the area. Now think of a two-dimensional triangle. So I'm going to draw a triangle here. It's equilateral, so this is L, L, L. Right? The question now is, how do we find the area of this? So in trigonometry, you learn an alternative formula for the area of a triangle. Okay? So this equilateral, so the three sides are the same. You know something more about this triangle. What do you know about the angles? And what are they? 60. So we also know that all the angles here are 60 degrees. Yes? Now in trigonometry, you learn a formula, an alternative way of calculating the area of a triangle, which is, so you can find the area, is 1/2 base times height. That's always true. But when you know two sides and the angle in between, you can calculate it. It's 1/2 the product of the sides times the sine of the angle in between. So recall, if you have a triangle, let's say this is A, this is B, and this angle is alpha. For a triangle like this, you can find its area by doing 1/2 A times B times the sine of alpha. Okay? And you should have discussed this back in trigonometry, and so they see the justification of why this is the case. If not, then you can ask me another time, and then I can show it to you really quick. But I don't want to use the time for that. The point is that this is an alternative formula for the area of a triangle, and that's what we really need to use right now, because we know we have the two sides and we have the angle in between. The thing is that I don't know the height of this. Okay, so that's why, I mean, you could calculate the height if you wanted to, because we know the angle. And equilateral triangles are special. When you draw a height, then the height of an equilateral triangle also coincides with the median and also with so the median is the one that splits the opposite side into equal pieces, okay? And also the angle bisector. So it's also the angle bisector of 60. So what I'm saying is, in an equilateral triangle, this is true for isosceles triangle. If you have an equilateral triangle and you draw this height, this is 90 degrees because it's a height, but because it's equilateral, everything here is the same. That means this is the same as this. So this is L/2, this is L/2. And also this angle is the same as this. So this is 30 and this is 30. So you know a bunch of stuff, okay? And then, you know this little side here, L/2, and you know the hypotenuse, you know the angles, you can find this one by using sine or cosine, whichever you like, okay? But instead of doing that, I'm just gonna use the original formula, which is 1/2 L squared times the sine of 60. Okay, we get the same thing regardless of what method you decide to use. Because L times L, okay? That's why it's L squared, and sine of 60 is square root of 3/2. So, moral of the story, and this probably, if you Google area of equilateral triangle, this is the formula that is going to pop up. Square root of 3/4 times L squared, okay? The 4 comes because sine of 60 is square root of 3/2, so 2 times 2 is 4, okay? So the 4 comes. So that's the formula for the area of an equilateral triangle, square root of 3/4 L squared. So of course you need to know the side. Now here we do know L, right? So in the picture we have L. Here it is. This is L, and you should understand that this is a function of x. Depending where x is, then L is gonna change. Now we need to come up with an expression for L. Can anybody tell me how can we calculate L with the given information? So we know that L is a function of x. How can we find it? If I tell you that x is equal to 1, what is L? How do you calculate it? Look at the picture. So let's say that you want to know what's L of 1. Meaning the slice is happening exactly here when x is equal to 1, right? How do you calculate L? Should I give you a hint? Think about what we did last time. Look at the picture. How do you find L?
It would just be L.
Top minus the bottom, right? So it's F minus G. You understand this? So if I give you x equal 1, then you find F of 1, G of 1, and subtract the two numbers. Yes? Just look at the picture. Remember, before we had a rectangle and we wanted to know the height, right? Now we have this little stick and we want to know the height of this. It's always, when it's like this, perpendicular, it's top minus bottom. If it was horizontal, you would do right minus left. Do you understand this? If the slice were taken like this, with respect to the y-axis, you will have to do right minus left. But here we're doing top minus bottom. So L of x can be calculated pretty easily. This is the top function, the bottom function.
In that situation, if you were to cut it parallel with the x-axis, which one would technically be to the right, since it's?
You will have to split into two intervals.
Okay.
You see? because you have to do the upper above the x-axis, because then the right is the red. So you would have to do it from 0 to 1. Now it will be with respect to y. And then below the x-axis, you do it from -1 to 0, but now the right is the blue. But that's why it's better in this case to do it like this, because with one integral, you're good to go. Good. All right. Does everybody understand that L can be calculated by doing F minus G? By looking at the picture. Just look at the picture. Do you understand that you can find that by doing top minus bottom? Okay. So let's put the formula. So F is 1 minus x over 2. And then G is, somebody saying something? He puts the little clock. That's interesting. Nobody does that. They usually just get up and do whatever, and they don't, but that's nice. Like a classmate saying he's gonna be back in a moment, and he puts the little busy thing. You know, that's good. All right, so I just put here my formula for F, my formula for G. I just want to combine these and subtract, so we get a nice formula for L, okay? All right, so L of x equals, so we're going to have 1 plus 1, we'll distribute the negative, so that's a 2. And then negative x squared, negative x over 2 minus x over 2, that's negative x, right? X over 2 plus x over 2, that's x. So L of x is given by the formula 2 minus x, and now that means that the area of our section is, remember the formula, square root of 3 over 4 L squared, so that's square root of 3 over 4 times 2 minus x squared. Are we okay with this? So now this is what we integrate, okay? I'll put that into my integral, and we are good to go. So the volume is the integral from 0 to 2 of square root of 3 over 4 times 2 minus x squared dx. Questions? Okay, so again, for this type of problems, you know, this is, I would say, this is the hard part. After this, it's just calculating the integral, and usually the integrals you're going to get here are straightforward integrals. We haven't done anything fancy yet when it comes to integrals. So now we just evaluate this. So I'm going to take out square root of 3 over 4, and then actually, just to make it easier, let me do a little substitution, and that way we keep practicing substitution. So I'm going to call u be 2 minus x, okay? Then du is going to be equal to negative dx, right? So then this integral becomes, I'm going to take out square root of 3 over 4. Then this would be u squared. Then is negative du, right? Dx is minus du. So I'm going to put the du here, and I'm going to put the minus outside. You okay with this? Now let's fix the limits. So when x is 0, u is equal to 2. And when x is 2, what's u equal to? 0. Now if you remember, we can always switch limits of integration, but then we get a minus. I'm going to use this minus to switch my limits. Yes? So now I'm going to use that minus to put the limits back. But we don't need to have a minus anymore. Are we okay with this? Now we integrate. So square root of 3 over 4 times, that's u cubed over 3 from 0 to 2. So we get square root of 3 over 12 times, now 2 to the 3, that's 8, and then 0. So that's 8 square root of 3 over 12, and we can simplify this. So we get 2 square root of 3 over 3. That's the volume. All right, questions? Yes?
Do we have to substitute with you, or can you just plug in for
Do the at this point, you do the integral however you want.
Is it more steps to just do it using you like that? Wouldn't it just be more steps?
Okay, how would you do that integral without substitution?
can't just plug in 2 and into the x value and 0 into the x value and solving it like that.
You need to find an antiderivative. You're doing an integral, so you have to integrate that function, right? You need to find an antiderivative. What's the antiderivative of that function? 2 minus x squared. Many ways to do it. Like you can expand the square and then, integrate the polynomial that you get. Or you could realize that you can just do 2 minus x cubed over 3, but then because of the chain rule, put a -1 in front. Many things. But I think with the use substitution, it makes it pretty simple to calculate the integral. Remember, the use substitution is meant to simplify the integral. I'd rather deal with u squared than deal with this. That's the point. But when you make a substitution, you have to change the limits, right? Always remember to change the limit. That's all. But at this point, you solve the integral however you want. So once you get here, it's up to you how you want to solve the integral. For example, if I'm grading something like this by hand, right? If it's not multiple choice and it's a work, half the points are already there, getting that formula. Then after that, the other half is, okay, show me that you can calculate the integral, right? You do it however you want. You have to get the same answer. Okay, questions? Did you understand this? So the whole point is in understanding the cross-section. For example, if I had told you that instead of equilateral triangles, the cross-sections are semicircles. The cross-sections are semicircles. They're semicircles. How would the problem change?
You would find half of and then the area of a circle, right?
Okay, but so what would be the formula? What formula do we integrate?
It would be 1/2 2
It's pi r squared.
pi r squared, yeah.
Right? The formula of the area of a circle is pi r squared. It's semicircle, so it's 1/2 pi r squared. But for this, we need r. What was r in this picture? Very good. And what tells you half of L? But okay, good. But in this case, so this is in general, but in this case, it's just F because this picture is symmetric. Does everybody see this? So really, the radius would just be this little piece right here, which is really L over 2. If this is somewhere else, then you will do F minus G over 2 because, but in this case, the top is the same as the bottom, so that would just be F. So you will have to integrate 1/2 pi F squared. That's what you would be integrating. If I had told you that the cross sections were semicircles, okay? So and then it will be a completely different integral and a completely different answer. So depending how the cross sections are, because then the solid changes, right? Then that's what you do. But the idea is always the same. Once you understand the region, then figure out what sort of area you need. So given the shape, you have to come up with the formula for that, and then that's the formula you integrate. So make sure that you know formula of area of triangles, of rectangles, of squares, of circles, semicircles, right? All of those common shapes, you need to know the area of, because they will be popping up in problems like this. You will see in the homework that you will have all of these options. Okay, questions? Okay, good. And then, as promised, let's do an example in which we actually, let's do something slightly more general, which is we're going to derive the formula for the volume of a square pyramid, okay? So prove that the volume of a square pyramid, and the reason why I'm doing this is because I want to show you that there are some techniques that you may want to use when you're trying to calculate, to solve this type of problems. We'll see in a second. So prove that the volume of a square pyramid is, anybody remembers? What's the volume? So if you have a rectangular solid, the volume is area of the base times the height. When it's a pyramid, it turns out that you can fit in 3 pyramids into that. So it's 1/3 area of the base times the height. Same thing with the cone. The cylinder is area of the base times the height. But if you have a circular cone, think of a party hat or an ice cream cone, it's 1/3 area of the base times the height. Okay? So it's 1/3 area of the base times the height, which let's call it 1/3 b squared times h, where in this case, because I'm saying that it's a square pyramid, you just need to know, let me just draw the picture here. This is what we have. So the base is a square. So this is what I'm calling B. Let's say this is the center of the square. And then we have our pyramid here. Okay? So as a pyramid with a square base, and then by B squared, I mean the area of the base, because it's a square. The area of the square is side square, right? And h is the height of the pyramid. This is h. Okay? All right, so let's do this. Okay, so if we want to figure this out, to justify this formula, then, you know, the idea is, okay, we have this solid, because this is a pyramid, it's a regular pyramid. So by regular, I mean that every time that I make a slice, your slice will always look the same as the base, okay? So if I cut this and discard the bottom, you end up with a pyramid, which is just a replica of what you had before, but smaller. That's what I mean by regular. All the sizes are compatible. In other words, the point is that the cross sections here are also squares, okay? So that's what we're gonna do. I'm gonna reuse the picture. Why are you disconnecting? But then let's put this in perspective. So I'm going to set the center of the pyramid to be my y-axis. Okay. And you know, and then the x-axis is gonna go through here. Okay, this is x, and this is y. And then the reason why I'm doing that is because then who can tell me what is this point of intersection with the x-axis in this picture? How much is this? So this is 0. So this distance is b/2, right? Remember, you will only see mostly letters in what we're doing, but we know b and we know h, because if I give you the pyramid, you know the height, and you know the base. You understand this? So capital B is a known quantity, it's a number, and h is a known quantity, okay? But we're doing this in general to figure out a formula. All right, so this right here is b/2. Yes? Okay, so now when we make a cut, I'm gonna make a cut like this. See, somewhere in here. Right, so you cut this and then you take out the cross section. That cross section is also a square. And then what I want to do is I'm going to integrate. I want to figure out the area of this square. I also need for my problem, because we're making the cut perpendicular to the y-axis, I need to know what this point up here is. Who can tell me what this is? At the top, the very tip of the pyramid. What's a number? Look at the picture. I set out my 0 to be at the base of the pyramid. So what's this point up here?
Oh, that's gonna be the height.
That's h.
Sorry.
Right? So our integral is gonna be from where? From 0 to h. Understand this? Because we are, notice how I'm doing the slices perpendicular to the y-axis. Okay? And so I'm moving like this in a vertical form from 0 to h. Yes? So now let's study that slice. Now the slice is a square. Right? So this is a square. The slice is a square, and then the square is going to have some size, so I'm going to call it s, little s. Okay? It's a square of side s. I want to figure out what this is with the given information. All right, so the first thing that I want, so first of all, notice that everything here is symmetric. So once again, you can think of here is the center of the pyramid. So if I know what is half of s, then of course I know what is s, okay? So I'm gonna work with half of this picture all the time. So let me get a picture from here. So it's a square, and so the area with respect to y is going to be equal to s of y squared, right? And why are we doing with respect to y? Because I'm making the cuts perpendicular to the y-axis. Yes? You understand this? So depending what y is, that would be my area. For example, when y equals h, what should be the area of this square? 0, right? There's no square. It's a point. If y is equal to 0, what should be the area of this square? My base, which is capital B squared, right? Now, what about in between? Okay, so that's what we're trying to figure out, a formula for that. So I just need to know what is S. I need a formula for S in terms of y, okay? Everybody understand this? And let's say that this is happening at the y level, okay? So let me draw a picture here. I'm gonna draw half of the pyramid, and I'm gonna draw the two-dimensional version of it. So this is how the picture looks. This is what we have. So just think of, there is a side here. I'm basically taking this triangle in my picture. Look, this is the triangle that I'm taking. Where the hypotenuse of the triangle is along this base of the pyramid. Do you understand this? Imagine making a cut like this, and then I'm just taking, you have a triangle like that, but then an isosceles triangle, but then I'm gonna take half of that triangle. So it will be a right triangle. Do you see that? Okay, so that actually means that this is, how much is this? That's b over 2. What is this? That's h. It's a right triangle. And also, my slice happened here, right? This is my slice. So let's say the slice happened over here. How much is that? This is s over 2. Everybody okay with this? The red side, this is s over 2 because it's half of the side of the slice. Again, everything is being cut in half. This, the original one is b, so it's b over 2. The original one here is s, so it's s over 2. You understand this? Okay, so we have this. Let's see, what else? Can you tell me how much is this? How much is this? So that, well, we don't, I mean, it appears to be half right now, but remember, the slice happen everywhere between 0 and h. So this is a general picture, it doesn't have to be halfway. In general, what is this? Who tell me this? This side. That's y, right? Remember, you're cutting like this between 0 and h. So whatever y is, that's what we're making the cut. You understand this? So that distance is given by the value of y. Yes? So that is y. So this right here is y. And therefore, how much is this? The top piece? Very good. So this is h minus y. So we are ready. So, and remember, from here, there are only two things that we don't know. What is it that we don't know? We don't know s, and we don't know y, because y is a variable. It's changing from 0 to 2. Our job is to write s in terms of y, so that's good, okay? Because we want s to be a function of y. But we know capital B, and we know h, okay? All right, so this is also a right triangle, and I want you to realize that we are in a situation with similar triangles. Just look at this small triangle here, and look at the big triangle. The small triangle is similar to the big one. Do you see that? Remember, similar means that they have the same angles. So this angle is the same for both of them. They both have an 90-degree angle, and then because it's only 180, this angle down here has to be the same as this one, right? So this little angle is the same as this one. So the small and big triangles are similar. Right here, small triangle is similar to the big triangle. And so when triangles are similar, remember the size, there is a proportionality relation among the sides, right? So so you just need to write the size that corresponds to each of the angles for one triangle, and then the corresponding size for the other angle. And here, I don't really care about the hypotenuse, so I'm gonna call this question mark, and this big one, I'm gonna call it 2 question mark. I don't really care about the hypotenuse. So the easy way to remember the proportionality is just write the 3 sides of one of the triangles. I'm gonna write, let's say, the small one first. So I'm gonna write h minus y, and then I'm gonna write here s over 2, and then here is the hypotenuse, which I don't know what it is, and then in the denominator we're gonna write the corresponding sides in the big triangle. What do I mean by corresponding sides? The ones that are opposed to the same angle. So in the small triangle, h over y corresponds to this angle over here. It's opposite to this little angle over here. So in the big triangle, this angle is the same as this one, so it corresponds to h, right? So h over y over h equals, now s over 2 corresponds to this top angle over here. So in the big triangle, what's the side that corresponds to this top angle? B over 2. Are we good with this? And then the hypotenuse that corresponds to each other, but I don't really care about that. We don't need that. Here we have everything we need. Now, because of this proportionality relation, from here, I can solve for S. That's what I'm gonna do. I'm gonna figure out what is S. So, by the way, notice that here, the 2's cancel out, right? And then we can update this, and we can write h minus y over h equals s over b. And now, solving for s, we get that s equals b times h minus y over h. You okay with this? All right. Now, this is, remember, b is a number, h is a number that we know. This is given to us when you're given the pyramid. So here is s, we don't know what it is, and here is our variable y. That's good. So if you tell me where the cut is, I can put that here, and with the known values of h and b, I can tell you what is s, the size of the slice. And that's all we need, really, because now this is the formula for the area of the slice, right? It's a square, so it's s squared. So we just need to square that quantity and integrate it, and we're good to go. So a of y equals b times h minus y over h squared, right? That's s squared. So that would be b squared over h squared times h minus y squared. I'm going to be integrating this formula. So the volume of our pyramid is going to be the integral from where to where? What are our limits of integration? From 0 to h. So from 0 to h of 8 of y dy, because this time our slices are taking perpendicular to the y-axis. So let's put our formula and get to work. Dy. All right, so remember, capital B and little h, these are constants, so I'm just going to take this out. Okay, so it's going to be b squared over h squared, the integral of, and then I'm going to play the same trick that I did before. I'm going to do substitution. Okay, I'm going to let u be equal to this guy just to simplify our integral. So du is negative dy. Okay, just like before, I put the negative in here, and then we're gonna get u squared du. Now let's fix the limits of integration. So when y is equal to 0, u is equal to h, right? And when y is equal to h, what is u equal to? 0. And just like before, what am I gonna do with that minus? I'm going to use it to switch the limits of integration. So we get b squared over h squared integral from 0 to h of u squared du. And now this is an easy integral to calculate. That's u cubed over 3 from 0 to h. So let's see. I'm going to keep my 1/3 here. Then my b squared over h squared. And then times, that would be h cubed minus 0, right? We plug in h, that's h cubed, and then plug in 0, you get your 0. So we have 1 over 3 b squared over h squared times h cubed. Then we see how h squared cancel with 2 h's in the top, and we only have 1 h, and we end up with 1 over 3 b squared times h as expected. 1/3 area of the base times the height. So that's how you obtain the volume of the pyramid. So all of those solids, all of those formulas that you were given back in high school, you can obtain those formulas via integration.
Would you ever ask us to prove?
I may ask you to prove another, not this one, but something similar. For example, the right circular cylinder is the same idea, right? Instead of a pyramid, what do you have? You have this shape, right? It's the same idea, but everything is exactly the same. It's just that when you make the cut, what do you get? You get circles instead of squares. But you will need to know the radius of that circle. How do you find the radius of that circle of the slice? Well, here is the radius of the base, and then you have your similar triangle situation. Here is little r, here is big R, this is h, right? And then you play exactly the same game. It's just that you have different formula. Instead of b squared, instead of, the psi squared, the formula you have to integrate is pi r squared, right? But it's the same idea, exactly the same. I can ask you something like this, or to find the volume of a sphere, right? But for that, that would be after we discuss solids of revolution. All right, so questions? Did you understand this?
So, Professor, I'm just wondering why you squared the s over there.
So,
Where it says AY and then you squared the s.
what's the slice?
So that
What's the shape of the slice?
it's a square.
And what's the area of a square? But what are the length and the width?
Length square.
Length square. But I'm calling the length, I'm calling S. If you see the picture, S stands for the length, like the side of the square, right? So the area is the side square. It's S squared. But then the whole point here is in figuring out S. Once you know what is S, then we're good to go. You square it and then integrate it. Right? Because the theorem says that once you know the formula for the area of the slice, if you want to know the volume, you just need to integrate this formula. Right? Okay. So we needed to get this formula, and that was the whole mess that we did above. Figure out what is this S. Right?
So basically, when you like have the area of the little slice,
Mm-hmm.
and then you integrate that, you get the volume of the whole thing.
Yes, that's what this theorem says.
Yeah.
Look up here. The volume can be calculated by doing the integral of the area. Where A is the area of the cross section. Cross section and slice is the same thing, right? The whole point here is usually to figure out the formula. What's A? Yes. That of, you mean of cross section?
Yeah, approving the formula for the cross section.
Why don't you do it?
Because it's hard.
So let's see. I'm gonna pick something from the homework. Let's pick one from the homework and we do it. Yes? Let's pick a problem from the homework. Let's see. Yeah. Anyways, we don't have time to start with the other stuff, so let's go ahead and do that. Because, for example, if you need to prove the formula, let's say, of a cylinder, you do exactly the same thing that we did. It's just that instead of a square, you have circles. But it's exactly the same idea. You have to use similar triangles and all of that business. It's exactly the same. Okay? So I don't want to repeat the same thing. So let's see. Let me actually let's look it up. Let's find something interesting in the homework.
Could we do the triangular pyramid?
I say let's find something that you're gonna see in the homework. There are plenty of problems in the homework. That way. All right, let's see. So problem number 1 is basically the same thing that we just did, but they're okay. Let me make it bigger. So problem number 1 is basically the same thing that we just did. It's a pyramid. It's a whole story, but at the end of the day, it's a pyramid. They tell you the height and they tell you the base, right?
They're not asking to prove it, they're just asking to find the cross section.
And what does it say here? Using
Yeah, you
integration.
find it using-
I mean, you find it using whatever you want. The idea is if you want to practice this, don't use the formula, use integration, right? Try to do it. I mean, at least you know what to expect as an answer. You can calculate the volume. 1/3 area of the base times the height. It's not a big deal. But can you find that same number using integration? That's the idea, right? So you practice what we just did. It's doing exactly what we did, but with concrete numbers. Instead of B and H, now you
Maybe
have.
doing that would make it better, because I think that the fact that it's not concrete numbers is confusing.
Well, but that's maths.
Okay, but let's try it. Help me
That's the
with-
homework. That's the homework. You do it. Let me do something different. I don't want to do the same thing twice. So let's see. Same thing. Find volume of a pyramid. Right. So the same thing. Okay. Here is a right circular cone. That's the same idea, like I said, with a circle. And I get something more interesting. Okay. So the base is the region bounded by this, and every cross section parallel to the x-axis is a triangle. Okay. So this is similar to the first example that we did. Similar, not the same because they are not equilateral. Now they're telling you that the base and the height are the same. Once again, you will use the formula 1/2 base times height. But since you have the base, because you see it in the picture, now you need to know the height, but the height is the same as the base. You're being told that here, right? So that's easy to do. I want to get to some in which they give you pictures. And I want you, for example, something like this. Equiangular is the same thing as equilateral. Equiangular means same angles. But the triangles that have the same angles are equilateral triangles, right? But, okay, let's do this one. I don't want to do triangles. I want to do something with semicircles. I think there's one here. Here it is. Okay, so the graph above shows the base of an object. Compute the sub value in terms of pi, so no approximations, of the volume of the object, given that the cross section taken perpendicular to the base are semicircles with their diameters on the base. In other words, we're taking the cross sections like this, okay? So perpendicular to the base, so this is the base. And then out of this picture, there are semicircles coming up. Do you understand this? Now, what's special about this problem is the fact that we are not providing any equations. We have to come up with the equations ourselves. But in this case, the shape is pretty easy, right? So it's a line. We know how to find equation of a line. I want to do it to remind you of these things, okay? Because otherwise, you will have like 4 or 5 problems like this in the home, okay? So
the cut is the semicircle.
yeah, so what you will see on the picture, when you cut, you will see a line here, which is the diameter, so a semicircle is the stuff sticking out of the board. You take your slice, this is the base, and what you take is the semicircle. That's coming out of the board, okay? And they told you here, the diameters are on the base, so that's what you see. So, you want to do this one?
Wait, Professor, can you scroll down a little bit to see if he has a video? Okay.
All right, but there could be videos in.
No, yeah, no, because if you had a video, like I would say not do this one because the video like explains it like pretty good. And,
Uh-huh.
Yeah.
Okay. So, do you want to do this one?
Yeah.
Okay.
Sorry.
All right, so let's use this little tool, take a screenshot. So when you want to take a screenshot, that's what you do.
You can tell you study computer science, have not seen another professor that's proficient in any technology.
So, yeah, nowadays, yeah, I know there are many that are banging their head. Times change. Okay, so here's the problem. So that's our example number 3. Okay, so by the way, when you do the homework, probably you're gonna, this is randomly generated, so you will get a different picture. Same shape, but with different data, so anyways, you have to do it. It's not like the answer that we get here is the same as what you're gonna get. The process will be the same. All right, so you understand what's going on, right? So we make, by the way, how many slices, how many intervals are we gonna need to calculate this? In 2 intervals, right? Because, for example, from 0 to 6, this is how a typical slice will look like, right? So you slice like that. This is our diameter. So we just, so the radius is just this half right here, but everything's fine all the way up to 6. The moment that we pass from 6 to 8, now we no longer have this top line and this bottom line, right? But then it's easy because we know exactly what the radius is. What's the radius in that case? It's a constant. It's always equal to 5, right? But the point is that we have to split this into 2 situations, okay? So we're gonna do it.
So you always do it at the halfway point.
What do you mean by the halfway point?
Like, how do you know where to split it?
Look at the picture. Where does the situation changes?
I don't know, because you put a red line over there.
Exactly. So we are slicing the solid perpendicular to the base. So we're slicing like this, right? So from 0 to 6, the situation is always the same. The top of the slice, so if you want to figure out the length of this, the top is always ruled by this line, and the bottom is always ruled by this other line, right? Yes, but the moment that we pass 6, now this line is gone. Now all of a sudden the slice is actually, this side is always the same thing, if you want, from -5 to 5. It's always 10.
So the cut is at 6, not at 4.
No, we are calling the whole thing.
Okay,
This is a typical, I mean,
all right.
forget about 4. I could have done this line here in 3. This is just a typical slice. What I want to say is that the slices from 0 to 6 are different than the slices from 6 to 8. From 0 to 6, the slices are changing. They are actually, they start pretty small, and then they start getting bigger and bigger and bigger up until you get to 6. Now, passing 6, you always have a consistent, the same slice along the way. Do you understand this? So that's why I will calculate 2 intervals, because from 0 to 6, we have one situation, and from 6 to 8, we have another situation. Do you understand this? Okay. I mean, the whole point is that you need to know what's the length of the length of this side, and then the picture tells you that you have to consider 2 cases. That one and this one. Okay. All right. So, but before we even do that, for my first integral, I need to know the equation of these lines, right? So let's figure that out first. So this is a line. The top, this is a line, and remember, lines have equations mx plus b. So, all you need are 2 points to find the equation of a line, but if you're lucky enough that you're given the y-intercept, you just have to find the slope and you're good to go, right? So we can do this the quick way. So let's do it the quick way. So both of these lines, let's just focus on the top one. What's the y-intercept of the top one?
0.
The y-intercept is 0, so that means b is equal to 0. So that line really has a form y equals mx. Yes, so we just need to figure out the slope, and to find the slope, just find 2 points that are on the line. For example, we have 0, 0, and we have this point over here, which is 6,5. Yes, so we can do right over wrong. So the slope is gonna be 5 over 6. Do you understand this? Or you can do y2 minus y1 or x2 minus x1. Use the formula, even the 2 points, whatever you want. The point is that the slope is positive 5 over 6. So the equation of that line is 5 over 6x. If you want, you may want to write this one. What's the equation of this other line? This little piece?
Just x equals 5.
Y equals 5.
5.
Yes? We're not gonna need it, but just as a general rule, you know, the shape changes, then you have to find the equation of all that. This one, we know what it is, x equals 8. So I'm just finding the equation of the boundary of my solid, okay? Now, let's find this one. Once again, this has the form mx plus b, but b is equal to 0, so just mx. Let's find the slope. The slope this time is negative because the line is going down, and this picture is symmetric. So we go down 5 units and then 6 units to the right, so it's negative 5 over 6, okay? So that's negative 5 over 6. X, and this boundary down here is y equals negative 5. Okay, so the volume that we're gonna do is gonna be split into 2 integrals. Everybody understand this? So our volume is gonna be the integral. Let's see, from where to where? from 0 to 6, and then I'm gonna call this a1 of x dx, because that's gonna have one formula for the area, and then plus the integral from where? From 6 to 8, and then I'm gonna say a2 of x dx. Okay. Now we know that the cross sections, they are semicircles, so all we really need to know is what's the radius of those semicircles. And in the picture, the radius is given by this portion right here, right? And then in the second picture, we know what's the radius. What's the radius here? Is equal to 5, right? It's always the same. So that one is easy. All right, so let's go here. For this one, the radius is given by the top function, right? Because this is just given by the top function. This is symmetric, so that's the halfway point. So R1 of x is gonna be equal to 5 over 6x. And then the second radius in the second picture is a constant, right? The radius is always 5. Do we understand this? So now and why am I doing this? Because now the slice, the area of the slice, a1 of x, remember, it's a semicircle. So it's 1/2 the area of a circle. What's the area of a circle? It's pi r squared, right?
I'm confused on how you got
What do you mean?
I mean, like,
That's the diameter.
uh-huh.
So because the problem says the diameter is what you see, so half of it is the radius. So the picture, this is symmetric, so half of, if you want, you do top minus bottom divided by 2. Okay, but because we see that the picture is symmetric, the top is just given by, the top half is given by the value of the function.
So it's just that equation.
5 over 6.
In whatever number.
5 over 6. But in general, if the picture was not symmetric, let's say that this line had a different slope,
Then
so
you
the
can
picture is not
subtract
symmetric, you need to do top minus bottom, that's the whole thing, and then divide by 2. That's how you find radius, right? Diameter divided by 2. The diameter is what you see. And in this picture, how do you find diameter? Top minus bottom, which is the whole thing. Do I need to write that down?
No.
No? Okay. All right, and in the second one, then, our second area is just 1/2 pi times 5 squared, right? So that's 25 pi over 2. Just look at the picture. The radius is what I show here as R1. What do you mean the value of the slope? The radius is not a constant. The radius depends on where you're making the slice. If you are very close to 0, you have a very small radius. As you start moving away from 0, your radius is growing. So your radius depends on this line. It depends on x.
That's why we put it as a function of x.
Yeah, depending what x is, the radius changes. It's a function of x, right? And the radius is being determined by this top line here.
Like 5 over 6 because of the.
5 over 6x.
Yeah.
You're saying, why do we have a 5 over 6? That's the slope of this line. I did rise over rho. So from this point, from 0, 0 to this point, that's 6,5. So go 5, 6 to the right.
We will always use the slope and then put it as a function.
Don't say always. It depends on the shape. If this is the shape, yes. but if the shape is different, right? You need to. It really depends on the shape that you're given. Right? Okay. Again, you're gonna have different problems in the homework, so hopefully once you start doing problems, this idea will be easier. So I'm gonna integrate those two, okay? So this is gonna be the integral from 0 to 6 of 1/2 pi, and then remember r is 5 over 6x. So I will be 5 over 6x squared. That's my first integral. Then the second integral is from 6 to 8. And then we have 1/2 pi. That's 25 pi over 2. We found the formula there. 25 pi over 2 dx. This one is easy. That's just a constant. So we can calculate this as put the constant out, and then you get x from 6 to 8, right? And then this one over here, I'm gonna put a pi over 2 out. Actually, then I have a 25 over 36 that I'm gonna put out as well, and then I only have my x squared in here. So I take out this pi over 2. This is 25 over 36 x squared. I took out also 25 over 36 and just left the x squared here, which is what I'm about to integrate. Okay. All right. So we get 25 pi over 72 times x cubed over 3 from 0 to 6 plus 25 pi over 2 times. Now this would be 8 minus 6, which is 2, right? So these 2's here cancel. And then here we end up with 25 pi over 72 times 3. And then I have to put 6 cubed minus 0, which is just 6 cubed, plus 25 pi. And now let's simplify this.
Professor,
Yes.
would you get that cube you just crossed out with? There's the one that you crossed
When
out.
you evaluate this, you evaluate 8. Remember, you have to do 8 minus 6. That's 2.
Okay.
Okay. You notice this is a constant, right? What does this mean? This x with the line.
Right, you like eight
That's
for
8
x.
minus 6, right? So you obtain this by doing 8 minus 6. Okay. All right. So let's see. What's 72 times? So 6 cubed. That's a 216. I'm gonna leave it as 25 times 216 pi over 72 times 3 plus 25 pi. So this 3 I can cancel with the 216, giving me a 72, and then the 72 cancel. Ah, nice. So that's 50 pi. It looks to be 50 pi. Let's see. Let me put the answer and make sure that that is, and then if you have questions, you ask me. Let's see. By the way, I'm more relaxed today because my wife's picking up my son. So that's why you don't see me running away. All right, so let's see. Hopefully you didn't make any mistake in there. Want to see the green stuff? Get the green stuff. It's always good to see the green stuff. So now we know it's correct, so ask me questions if you have. Okay, so before we get to, if you have questions to about the algebra, before we get there, let's first make sure that we understand the setup. Do you understand how we obtain these two intervals? Is it clear? So is it clear how this one was obtained? Because the radius is the same from 6 to 8, and it turns out to be the radius is 25, right? It's 5. But then the formula, remember, is 1/2 because it's half a circle, pi r squared. That's where the 25 is coming from, pi squared. Okay? So we integrate that. So the second integral is not a problem. That's 25 pi. Now the first integral, I mean, if you don't have questions, I'm not going to repeat the same thing. But you know, the radius is half of what we have in the picture, which is given just by top function, pi over 6. So remember, when you're doing these problems, you have to figure out the formulas for the boundaries, okay? So you can obtain this. All right. Any questions? No? Okay, so with this, you should be able to do what you have in the homework. Now, in the homework, there are some questions, like towards the second half of the homework, that it requires a solid revolution. That this method, we're gonna do this next week, okay? So there will be some problems that you may, if you don't remember this, or if you have not done this, you're not gonna be able to do just yet, okay? So on Tuesday, we will discuss that. But we have good stuff to work on right now. Like I think when we start going to, you see here, starting question 10, this is start asking you question about stories of revolution. We will discuss this on Tuesday. So up to question 9, you can do it what we discussed today.